Well, hey there. Good morning, good afternoon, good evening, or maybe even good night. This is Dr. Franklin, and I'm back again with another video that's going to talk about Cohens D. Cohens D specifically deals with calculating the effect size for a significant result that you obtained in step 4 of hypothesis testing. So I do want to briefly highlight the difference between statistical difference and practical difference. So when we obtain a statistical difference as it relates to a z-test or a t-test, we are simply obtaining results that are very unlikely to occur if there is no treatment effect. That's what that alpha level represents. There's a 5% chance that the null hypothesis is correct and that there is really no treatment effect. So tests are making a relative comparison. That is, the size of the treatment effect is being evaluated relative to the standard error. The standard error is the average variation that you should expect within a population as represented by a sample. Now, a problem ensues in that if the standard error is small enough, in other words, if there's not a whole lot of variation to begin with, then the treatment effect can be small and large enough to be significant. So ultimately, a hypothesis test evaluates the relative size of treatment versus the absolute treatment effect. And let me show you an example that illustrates this. So let's say we're calculating some z-test as it pertains to two separate layouts of statistical information. So we got a population mean of 50, population standard deviation of 10, a sample mean of 49, and a sample size of 25. Now we are going to move forward to calculate a z-score for each of these samples, and this is the formula for doing so. So our first step would be to calculate our standard error of the mean, which would consist of us dividing the population standard deviation by the square root of the sample size. If we were to do that out as it relates to the first sample statistics as it relates to the set at the top of the page, we would have 10 in the numerator, and then in the denominator we would have 25. If we do that out, we'd end up with 5. 10 would be over it, and then if we did that division out, we'd end up with a standard error of the mean of 2. Then if we ultimately plug that into our z, we will end up with the following. So we'd have 49 minus 50 over 2. Once we do the numerator out, we would end up with a negative 1 over 2, and then finally we would end up with a negative 0.50. Now let's move to the bottom and do the standard error of the mean for the bottom sample characteristics. So if we calculate a standard error of the mean for it, we'd have 10 in the numerator over the square root of 49. Take the square root of, I'm sorry, not the square root of 49, square root of 500. If we take the square root of 500, we would end up with 22.36 with 10 over it. Divide that 10 by that 22.36 and we'd end up with a 0.45. And then finally we do our z, where we would have 49 minus 50 over 0.45. We do that equation out. This is what we'd look like. And then finally we'd end up with a negative 0.222. Now I did all of that to show you that when the variation within a sample's characteristics change, there's a greater likelihood to reject the null hypothesis even if your difference is very small. We know that our difference is very small because when we take 50 from 49, we end up with a negative 1 in both instances. So we're only talking about a 1-point difference across the population mean and the sample mean. And these data sets are pretty much the same with the exception of what happens when we get to our sample sizes, and that ultimately affects our variation. Now, same mean difference, but look, the variation is different. So in the standard error of the mean located at the top of the page, this is larger, and thus our z is smaller. And if we were going to use a plus or minus 1.96 with an alpha level of 0.05 and it was a two-tailed test, and we were trying to evaluate if this z was statistically significant, we wouldn't be able to say it was. However, this variation is much smaller. As a result of the variation being smaller, we see that according to those same standards, right, 0.05, two-tailed test, ultimately we would end up rejecting our null hypothesis with this particular setup. Okay, why are we rejecting our null hypothesis with this particular setup? Because ultimately the variation was smaller, so even minute differences can churn out significant differences when comparing sample means with population means. So variation affects whether or not you get statistically significant results, as well as sample size affects that. So the goal of calculating effect sizes is to measure and describe absolute size of treatment effect in a way that is not influenced by the number of scores in a sample. And one of the ways that you can do that is by using the Cohens D. The mission is essentially to regress to a population standard deviation in an effort to standardize the mean difference in much the same way that z-scores standardize locations in a distribution. So let me erase this information, which was mainly put into play to highlight how variation and sample size affects the likelihood of obtaining significant differences. And let me give you the basic formula, and this is in a very general sense, the basic formula for calculating Cohens D. Cohens D is the mean difference over the standard deviation. And we'll talk about what that looks like specifically for a z-test, what that looks like for a one-sample t-test, and what that looks like for a two-sample t-test. Finally, I will give you criteria as to how to evaluate or interpret the treatment effect as it relates to a significant difference that you are finding with the statistic that you calculated. So presented on this whiteboard, I have a breakup of the different types of statistics that you could calculate in step 3 of the 4 steps involved in hypothesis testing. So I have the z-test listed, the one-sample t-test listed, the two-sample t-test listed, and magnitude of D. Magnitude of D is specifically dealing with how you would go about calculating Cohens D. So if you end up with a numeric that is around 0.02, then you would say that there is a small treatment effect. If the numeric is around 0.5, you would say that there's a medium effect. And if the numeric is around 0.8 or higher than 0.8, you would say that there is a large treatment effect. Now, let's start with the z-test. As you can see at the top, underneath the header, I have the formula for Cohens D, which is the mean difference over the standard deviation. And I placed directly below it sample characteristics as it pertains to our earlier discussion about magnitude and how how sample size affects the likelihood of finding a statistical significance. So we ended up with a negative 2.22, and we found out that the independent variable was significantly impacting the dependent variable in this case, or that the sample mean is markedly different from the population mean. However, we know that there's only a 1 point difference. So we can assess the treatment effect by taking the mean difference, which is -1, and putting that over your standard deviation. In this particular case, your standard deviation is 10, your population standard deviation. So when you do -1 divided by 10, you end up with 0.10. And that 0.10 is of course negative, but the signage doesn't really matter. What you'll be focusing on is the absolute value, or just a number, and when you go to describe that treatment effect, you will say that it is a small effect because that 0.10 is very close to 0.02. Now moving forward, we have the Cohens D formula for the one sample t-test, and that formula is the mean difference again over standard deviation. Now just abbreviated standard deviation with the lowercase s. Now let's say we were given these characteristics as it pertained to a sample, population mean, sample size, a sample mean, and a sum of squares. And let's say we went through all of the steps as it pertained to calculating the one sample t-test. So we calculated a variance, we calculated a standard error of the mean, and then we finally got to a t, and we found that our t was significant. We know it's significant because our t calculated is -4.39, and our t critical, which is likely two-tailed alpha 0.05, that information is usually given to you, that 2t critical on the negative end is being exceeded by this t calculated, which is a -4.39. Now we want to assess if the treatment effect is small, medium, or large. We could do this by simply putting our mean difference in the numerator. So we would go Cohens D equals, let's say the mean difference was 10 minus 15, right? So you're basically taking the numerator of your t and putting that into the numerator of your Cohens D. So we got 10 minus 15, which gives us a -5. And then we need to put our standard deviation in the denominator. Now, we can give the standard deviation by simply taking our sum of squares, which is 94. So we take our sum of squares and we divide by degrees of freedom, and then we're going to take the square root of all of that to end up with our sample standard deviation. So that would leave us with an 8 in the denominator, 94 in the top. Then we got to take the square root of it all. And when we do 94 divided by 8, we end up with 11.75. And then when we take the square root of 11.75, we end up with 3.43. Okay, and 3.43 is the standard deviation. So we'd plug that in the denominator, and from there we're going to do -5 divided by 3.43, and we will end up with 1.46. That is if we round it to the hundredths place. Now, this 1.46, if we go to this magnitude of the D column, we will quickly realize that this is a large treatment effect. So this significant difference that we found here was not simply due to the sample size or the standard deviation necessarily, but was due to the effect of the independent variable, some manipulation of the independent variable or the treatment, TX in abbreviation, that led to such a big impact in the dependent variable. Finally, with the two-sample t-test, okay, let's say that we've gone through all of our steps in terms of calculating this two-sample t-test. So we've gotten a pooled variance, we've gotten the standard error of the difference between the means, and we calculated our t-calculated for the two-sample t-test. We found out that our t-calculated was a negative 2.67, and the t-critical region boundary markers was 2.145 below the mean and above the mean. We made a decision to reject the null hypothesis because ultimately that 2.67 in terms of the absolute value exceeds that 2.145. Now we want to know if we have a significant treatment effect. Cohens D for the two-sample t-test is the mean difference in the numerator. So you're essentially taking this, okay? So here we have 12 minus 8 over your pooled variance. So your pooled variance in regard to this sample would involve you doing this formula here, basically taking 60 plus 66, which would yield you 126, and dividing by 14 because that is your total degree of freedom. And from there you will put 9 in your denominator. Now it's important for you to remember to take the square root of that pooled variance. So let's move forward and finish this equation. 12 minus 8 is 4 over the square root of 9. That will give you 3. And then when you divide that 4 by 3, you will end up with 1.33. Now, based on the classification to the right margin, this would be a very large treatment effect. Okay, so let's recap. Okay, how would you go about getting Cohens D for a z-test in which you had a significant finding? Well, you would simply take the population standard deviation, which is 10, and drag that down into the denominator of your Cohens D formula, and then you take the numerator of your z-test formula, that mean difference, 49 minus 50, negative 1, drag it down, do that equation out, and you would end up with 0.10. This would produce a small treatment effect, even with the negative there. Focus should be placed on the absolute value and not necessarily the signage. So this would be a small effect because that 0.10 hovers closer to 0.02 than it does to 0.05. Now, how would you go about calculating one sample t-test in Cohens D? Well, the one sample t-test formulas are listed out: variance, standard error of the mean, and then a calculated t. If you found a significant finding, then you move on to Cohens D, which is mean difference over the standard deviation. And in this particular example, you would need to take your variance that you would calculate based on the sum of squares that's provided you, and you need to take your variance, take the square root of it, and once you took the square root of it, it would be the standard deviation that you need in the denominator of your Cohens D formula. Okay, you take the mean difference that you found in the numerator for your calculated t, drag that down, and as you can see, you will end up with all that you need to calculate your Cohens D. This yielded a large treatment effect because it is closest to 0.8 than it is to any of these other magnitudes listed. And then finally, calculating Cohens D for a two-sample t-test involves taking your pooled variance, dragging that down into your denominator of the Cohens D, and taking the square root of it, getting 3, and making sure that you're dragging your mean difference down into your numerator of the Cohens D, and ultimately dividing your mean difference, that 4, by the square root of your pooled variance to end up with a 1.33, which is a very large treatment effect. So in general, in terms of interpreting the Cohen's D, keep in mind that anything around 0.02 is a small effect, but once you start getting beyond 0.25 and going up towards zero point 0.5, then it's proper to labelize any treatment effect numeric you get as a medium effect. You can keep classifying things as medium as long as it spans from 0.5 to 6.5, but the minute it starts going over 6.5 and it starts creeping towards zero point 0.8, that numeric can be labeled as a large treatment effect. Of course, anything higher than zero point 0.8 would be a very large treatment effect. So I hope that this was helpful. Feel free to leave me comments, questions, and concerns below in the comment box, and I look forward to interacting with you soon. Take care.